Hello everyone. Today we'll start the second part of coordination compounds, class 12. In this video we'll discuss Werner's theory. So, Werner's coordination theory. Who was Werner first? Werner was a Swiss chemist who was awarded Nobel Prize in 1913 for his theory for the coordination for his coordination theory. He is considered as the father of coordination chemistry. Okay, so how he discovered all this? Werner, being a chemist, he was working on cobalt 3 chloride ammonium complexes. So basically, he was working on some complexes which included cobalt plus ammonia plus chloride ions. So what he wanted to do, he wanted to neutralize this ammonia by adding HCl. So he was adding HCl, but he couldn't neutralize the ammonia. Hence, he observed that upon addition of hydrochloric acid, he observed that ammonia could not be completely removed. He wanted to remove ammonia from his reaction mixture, but when he added acid, he could not remove that. Why is it so? Then he figured out that maybe metal is coordinated with ammonia strongly. That means there is a strong bond between them. Okay. So he said that maybe it could be like ammonia must be bound more tightly to the central cobalt ion. So to further understand that, he added aqueous silver nitrate. Silver nitrate is AgNO3. If you are adding silver nitrate to a complex containing cobalt plus ammonia plus chloride, what will one expect? It could be expected as no, that silver will combine with chloride ions. Silver and chloride ions might combine and form AgCl. So, with the complexes that he was working, he observed that solid silver chloride formed. This AgCl PPT started coming out of the reaction mixture. So from there, he concluded that he calculated the amount of silver chloride. So he was working on certain complexes. Some complexes contain 2 chlorides, some complexes contain 3 chlorides, some complexes contain 1 chloride. So when he added silver nitrate to all of that, so he found that in case of 2 chloride complex, he obtained 2 AgCl. In 3 chloride, he obtained 1 AgCl, 3 AgCl. Similarly, for 1 chloride complex, he obtained 1 AgCl. So from here, he concluded that the amount of AgCl coming out depends upon depends upon how many chlorides ion are there in the reaction mixture. So, for example, if we considered cobalt chloride dot 6 ammonia, then 3 chlorides were converted out. 3Cl were 3Cl were converted into AgCl. But for the similar, if we considered cobalt chloride with 5 ammonia, only 2 chlorides were outside as a PPT. Why is it so? We'll understand this in next slide. So similarly, when he worked with cobalt chloride with 4 ammonia, he found out that only one product, one of the 3 chloride precipitated as silver nitrate. It was happening because the complex that contained 6 ammonia and 3 chloride ion, basically there the formulation was, it was actually a coordination compound. He was the first one to observe that ammonia is coordinating with cobalt and is forming an octahedral complex where 6 ammonia molecules are coordinating to the cobalt, and the chloride ion is actually present as a counter anion here. In the previous video, I told you that there is a coordination sphere and the counter ion. So with the yellow complex that he was working that contains 6 ammonia molecule and 3 cobalt ions, he found out that He was the first one to observe this coordination compounds. He found out that the ammonia is actually forming a coordination bond with cobalt and is bound strongly. When he added silver nitrate to this complex, he observed that silver ion along with this counter anion formed 3 AgCl molecule as a PPT. So you can see there are three molecules over here. Similarly, for the complex, this purple complex that contain five ammonia molecule and three chloride ions. For this one, what he observed, let me change the pen. He observed that cobalt with contained five ammonia molecules. So five ammonia molecules were there. One, two, three, four, five. So five are there. But in the previous video, I told you that the cobalt, these coordination compounds are either octahedral or they are tetrahedral. So these complexes, cobalt ammonia complexes are octahedral. So to complete the octahedral geometry, one chloride from outside came inside the coordination sphere and one chloride bound to the cobalt ion forming this complex and two chloride ions are outside as counter anions. So, when silver nitrate was added to this complex, it was observed as only the two chloride anions acting as counter anions, only these two formed PPT with silver ion, and only two molecules of silver chloride were observed as PPT. As you can see in this table, only two molecules came out. Similarly, for the green complex that contained four ammonia molecule, sorry, that contain uh, let me take the green pen only. So with, for that complex where there are only four ammonia molecules. So four ammonia molecules are coordinated to the metal and three to complete the coordination, six coordination that is hexa coordinated cobalt complex. So, two chloride ions were inside the coordination sphere and only one chloride ion was outside the coordination sphere. To this complex, when silver nitrate was added, it was observed as only one molecule of silver chloride came out. This only one ion is present outside the coordination sphere as counter anion. Only this molecule combined with this silver ion and formed one AgCl PPT, as you can observe here. Similarly, for the cobalt anion, for this cobalt chloride dot 4 ammonia molecule, he obtained two color complexes. One was green and one was violet. So how he obtained that one? The violet one was the trans isomer basically. One is cis and one other one is trans. So the other one was chloride and chloride was in trans position and four ammonia molecules were like this. Here also, depending upon the position, the color change and one chloride was present outside and with silver nitrate, it formed one molecule of AgCl. So here he observed that with different composition of reaction mixture containing different amount of chloride ions, he was getting different amount of silver chloride precipitate. That explains these coordination compounds where a ligand is coordinating to the central metal ion via strong coordination bonds. These are the strong coordination bonds. Chloride is binding here via coordination bonds and the rest of the chloride ion is present outside the coordination sphere and only those ions which are present outside the coordination sphere, these are coordinating with the silver ion of silver nitrate and are forming silver chloride as PPT. I hope you guys are understanding what I'm trying to explain. So, these were the initial experiments performed by Werner, where he observed that for different complexes that he was working, different amount of silver chloride came out, and from there he gave this coordination complex theory that complexes are there where ligands are coordinating strongly to the metal ion, and those with ions which are present outside the coordination sphere, they are basically reacting with silver nitrate to form silver chloride PPT, and depending upon the silver chloride obtained, he gave this formulation that this much chloride ion might be inside the coordination sphere and the rest could be outside the coordination sphere. Okay. So, the resulting observation suggests that the complex or the coordination compounds in the inner coordination sphere, that is the inside the coordination sphere, which is also referred to in some texts as first sphere, ligands are directly bound to the central metal ion. These ammonia molecules are directly bound to the central metal ion. And in the outer coordination sphere, considered as this counter ion, some this chloride is considered as outer coordination sphere. Okay, and this those which are directly bound to the metal ion, this ammonia molecules are considered as inner coordination sphere. Inner coordination sphere. So in the outer coordination sphere, sometimes referred to as second sphere, the other ions are attached to the complex ion. These are basically chloride ion is attached to this complex ion having +3 charge. Okay. Werner was awarded Nobel Prize for in 1913 for this coordination theory, as he explained that ligands, there is a bond formation between metal and ligands via coordinate bonds. That's why the theories, the complexes are called coordination complexes. So this is a Werner's coordination theory. Werner explained the nature of the bonding in the complexes, that ligands are coordinating with the metal ions and are donating their lone pairs to the metal ion via coordination bond. He explained the bonding, and he further gave some postulates which are considered as the postulates of Werner theory. The first postulate was metal shows two different kind of valencies, primary valency and the secondary valency. Okay. So as you know that in a coordination complex, a metal is there and there is an inner coordination sphere. Inner coordination sphere is where your ammonia molecules were present with the cobalt ion. As you can see in this figure, the cobalt ion is present as a metal inside central metal ion, and the ammonia molecules are present in the inner coordination sphere. Okay, and the outer sphere is the ionization sphere, which where the chloride ions are present, which are outside. These are not directly, okay, just a minute. These chloride ions are not directly linked to the cobalt ion, but they are just satisfying the charge over the cobalt ion. Cobalt ion has +3 charge, so each chloride ion with -1 charge, three such chloride ions are balancing the charge on cobalt. So metal, first theory was that metal shows two different kind of valencies, a primary valency and the secondary valency. Okay, the ions bound to the secondary linkage to the metal ion have characteristic spatial arrangement corresponding to different coordination number. As you can see, these ammonia molecules have a characteristic arrangement. These will bind in coordination number of 6 or 4. And here you can see these are arrangement is an octahedral arrangement. Similarly, the most common geometrical shapes in coordination compounds, as I told in the previous video as well, they are octahedral, square planar, and tetrahedral. These were the three postulates given by Werner in his one theory. So, primary valency. When we define there that in a coordination compound there are two ions are arranged in that there are two kinds of valency. Metal shows two kinds of valency. So, we'll discuss primary valency first. Primary valency is normally ionizable. Okay, the chloride ions present outside could be said as primary valency. They are equal to the positive charge on metal ion. As you saw in the complex cobalt, ammonia, ammonia, cobalt hexa ammonia trichloride complex. So in this complex, if you consider, okay, this is the inner coordination sphere I draw with a blue pen. And with the red pen, I'm drawing three chloride ions. So these chloride ions are not directly attached to the cobalt metal ion, central metal ion, but they are basically satisfying the positive charge on cobalt, that is +3. Okay, these are ionizable. Ionizable means when I am adding water to this, I'll get inner coordination sphere, that is a coordination sphere containing cobalt plus ammonia, 6 molecules of that having 3 plus charge plus 3 chloride ions. So if I am adding water to a coordination complex, here I'll get total 4 ions. One is this one and one is three of these counter ions. So these primary valency, these chloride are considered as primary valency here, as they are ionizable. They are basically balancing the charge on the central metal ion. These three chloride ions are balancing the charge over here, and these valency is satisfied by the negatively charged. Mostly these are, since they are balancing the charge, so metal has a positive charge. In order to balance this positive charge, you need to provide some negative charge. So negative charge will be provided by these primary valencies that will act as counter anions. For example, okay, in chromium chloride 3, let me erase the screen. Okay, so in chromium chloride 3, the primary valency is equal to the 3 chloride ion, because chromium has +3 charge, and these chloride ions are balancing that. It is equal to the oxidation number of central metal ion. As you can see, the 3 is basically balancing the +3 charge over here. It is equal to the oxidation number. Coming to the secondary valency. Secondary valency are non-ionizable in this complex, that is cobalt, ammonia, 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 6 ammonia hexa ammonia complex, cobalt hexa ammonia complex. We can write a coordination complex in this version. This is the coordination sphere, this is the counter ion, this is the central metal ion, counter ion, coordination sphere. So why I'm saying it is non-ionizable, I am adding H2O, what will I get? I'll get this coordination sphere with 3 positive charge plus 3 Cl minus ions. The secondary valencies are basically satisfied by the ligands that are directly attached. The ammonia molecules are directly attached. These are non-ionizable. They won't dissociate in water. Coordination sphere itself won't dissociate. Cobalt ions and ammonia molecules won't dissociate in water. They will stay intact as a coordination entity, as a, this will exist as a whole ion. Ammonia molecules won't separate out from this. These are non-ionizable. Though, so secondary valency is basically over here is satisfied by ammonia molecule. Okay. The secondary valency equal to the number of the ligands, as you saw that in cobalt, ammonia 6, Cl3. Secondary valency is equal to number of ligands. Secondary valency is satisfied by the ammonia. So here the secondary valency is equal to the number of ligands. It is also called the coordination number. Okay, here ammonia coordination number is 6, and 6 are the secondary valency. Okay, the common satisfied by neutral or negative charge, or sometimes could be positive charge as well. For example, in this complex cobalt, ammonia, ammonia, ammonia. Let's say one chloride is there, ammonia, ammonia, and Cl2 outside. So tell me, is this a chloride? Is this chloride ion is a secondary valency or primary valency? Basically, this chloride ion is acting as both. It is acting as secondary valency. Here, in this case, as you can see, the chloride ion is directly attached to the cobalt ion. It won't be dissociated. It won't get ionized, but it is also balancing the charge. on the cobalt ion. So this chloride ion present inside, even though it is not ionizable, it is secondary valency, but it is also balancing the charge on the cobalt ion. Okay, it could be negatively charged. For this complex, only two chloride ions are outside, and these are the primary valency, and this will be considered as secondary valency. So, for now, we understood that Werner gave a theory where he defined that in a coordination complex, there are two types of valencies, primary valencies and secondary valencies. Primary valencies are present outside the coordination sphere, and secondary valencies are present inside the coordination sphere, and both primary and secondary valencies satisfy the charge on the metal ion. Okay, so what were the evidence? Till now, he proved by silver nitrate experiments. No, he added silver nitrate to metal complex. For the metal complex, okay, for some metal complex, let's say X were inside and some chloride ion Y were outside. So when he was adding silver nitrate, he observed that he was getting Y amount of silver chloride. Okay, because only those which are outside, only that will be precipitated. So what evidences he provided? He performed cryoscopic measurements. Cryoscopic measurements, you must have read that chapter, solution. In the chapter solution, you have heard about the, no, in the colligative properties, you have heard that colligative properties like depression in freezing point or elevation in boiling point or osmotic pressure, they all depend upon directly proportional to the number of moles. So here, depending upon how much moles of chloride ion converted to the silver chloride ion, would depend counting the amount of chloride, silver chloride precipitate, he concluded the composition of the metal complexes. The cryoscopic measurements gives the number of ions formed by the dissociation of ionic compound. Basically, depends upon the number of moles. So depression in freezing point is a colligative property. As we know from the colligative property chapter, the solution states, and the depending upon the number of particles in the solution, greater the number of particles, the more will be the freezing point. For example, now you tell me that this is a complex hexacoordinated complex, three chloride ions are present outside. Let's say this is my another complex. So this is a hexacoordinated complex, five ammonia molecule, one chloride ion. Another one I'll give you a hexacoordinated complex with four ammonia molecule and one chloride ion. So depending upon the freezing depression in freezing point depends upon the number of ions. So here count the number of ions. H2O, H2O, let's say these are present in water. So count the number of ions. Here what will be the dissociation? Cobalt ammonia 6 plus 3 plus 3Cl minus. Okay. Here the dissociation will be like cobalt ammonia 5Cl. This inside one will not dissociate. So it will give 2Cl minus cobalt ammonia 4Cl2 plus 1 will give 1Cl minus ion. So these will be the dissociation pattern. So count the number of ions over here. 3 chloride ion and 1 complex ion. Total number of ions are 4. Total number of ions are 2 plus 1, 3. 1 plus 1, 2. Number of ions are different. So here number of 4, number is 3, number is 2. So their depression in freezing point will be different because depression in freezing point is directly proportional to delta TF. You know the delta TF. Delta TF is directly proportional to number of moles of ions or number of particles. It is depending on number of particles. So here the depression in freezing point will be different because we are seeing different number of ions dissociated. That's how he provided the evidence. For example, the same thing that I was explaining in the previous slide. So in the first complex, this one, the composition is cobalt ammonia 6 plus 3Cl minus. Okay. In this cobalt ammonia, you have to complete the coordination, the six coordination. So five ammonia will be present inside, one chloride will be present inside to form the six coordination, two chloride ions will be present outside. So five ammonia here, there will be four ammonia, 2Cl minus plus 1Cl minus outside. Cobalt ammonia here, in order to fulfill that six coordination thing, you there will be no chloride ions present outside. So count the number of total ions: 4, 3, 2, 1 only. So as the number of, it should be 1. Why it is written 0? It should be 1. One ion is there. No, this is one ion. This and this. But if you see, it is a neutral molecule. Charge is 0, but that doesn't mean it won't ionize. Actually, it is okay. It is okay to 0 because it won't ionize. The +3 charge on the cobalt is balanced by -3 charge, so overall it is 0. It is a neutral coordination complex. So number of ions will be 0, but the overall it will stay like this only. So the number of particles will be like this. As the number of particles are increasing, the depression in freezing point is directly proportional number of particles. So number of depression in freezing point will be more as we go in this direction for the complexes. The other evidence that was provided by Werner for his coordination complex theory was electrical conductance measurement. As you know, electrical conductance is basically due to the movement of electron. Movement of electron. Okay, movement of electrons or ions. Okay, if more ions are present, more ions, more current. Hey, if you have five ions, there will be more. Let's suppose there is 5I current. I am considering 5 ions. Current will be due to 5 ions. If I am considering 2 ions, current will be 2I. So 5I is greater or not. Similarly, depending upon the number of ions released, the current will be more. So what he said, the conductance of the solution, he said the conductance of solution depends upon the number of charged particles present in the solution. For example, for this cobalt ammonia chloride ion, the dissociation will be cobalt ammonia plus. It is 3 plus basically, and 3 Cl minus. Okay. And here it is plus 2 charge over this complex. So this is the complex dissociation pattern and this is the dissociation pattern. Number of ions in this upper one will be, number of ions here are 4, 3, 2. More number of ions, more will be the current. So more conductance of the compound should be followed, which is satisfy the observed conductance value. So for the first one over here, this one, the 4 ions will be there. There will be 3 ions for this. There will be 2 ions for this. There will be no ion for this. There is a neutral molecule. So the conductance will go in this fashion. Third evidence that he provided was precipitation reaction. Precipitation, the same that I explained in the previous slides, that he added silver nitrate, and by adding silver nitrate, he observed that by see, he was adding silver nitrate, and the molecules which were present outside, the chloride ions that were present outside, only that chloride ions formed silver chloride. So from there he got to know the composition of the these complexes. So on addition of silver nitrate solution with chloride complexes, the chloride ions which present outside the coordination sphere undergo precipitation reaction as a number of chloride ions present outside the coordination number increases, the number of formation of precipitate increases, and vice versa. Please refer to the previous slide over here. Over this slide, you can see that here three chloride ions were present outside. When added silver nitrate, three AgCl molecules came out. In the second one, two chloride ions were present. Only two molecules of silver chloride precipitated. In the third green complex, only one molecule of silver chloride came out. So, by this thing, he concluded, he provided the evidence. So, and now you can say that by cryoscopic measurement, that is the depression in freezing point, which depends upon the number of ions, the number of the molecules, by electrical conductance, which again depends upon the number of ions movement, and by the precipitation reaction, where he found out the calculated the number of silver chloride precipitates, he concluded the composition of the metal complexes, that how many chloride ions are inside the coordination sphere and how many chloride ions are outside the coordination sphere. Only those chloride ions that are present outside the coordination sphere, only they will form PPT, they will get ionized. Hence, he gave this theory of primary valency and secondary valency. Limitations of Werner theory. Every theory has some limitations. It was 1913 when Werner, it was basically 1913, and today it's 2022. So by 1913, Werner proposed this theory. So old, like more than 100 years. So by that time, so he proposed this theory that contains there is a primary valency, then there are secondary valency. Primary valency are ionizable, and secondary valencies are not ionizable. Okay, so he gave this theory and provided evidences by depression in freezing point, delta TF, electrical conductance measurement, current measurement, and silver chloride PPT reaction. He provided the evidence and won a Nobel Prize. He is considered as the father of coordination chemistry. So, but his theory again consists of some errors that were the limitations, and he was further that were further modified by other theories we'll discuss in the next video most probably. So the limitation of the Werner theory: though Werner explained some properties of the coordination compound, he failed to explain the color of the coordination compound. As you saw that in case of cobalt complex containing two chloride ion present outside, this ammonia and this ammonia there could be two formulations, cis one and trans one. One of them was green color and other was violet color. Violet was one where chloride was present in the trans manner. So these are ammonia. He couldn't explain like why this is the color for this compound and this is the color for this compound, even though the composition is same, but due to the fashion of binding fashion, he could not explain the color. That will be satisfied with the another theory that will explain later. Uh, so this was one of the limitation of the Werner theory. Second limitation was he could not explain the magnetic and optical properties of the coordination compound. So magnetic properties are those that depends upon free electrons. Okay, he could not explain those properties, but later on, a valence bond theory came. That theory came that somehow explained the magnetic properties. We'll discuss that later. He could not answer the question: why does coordination sphere have a definite geometry? Why only coordination complexes are forming tetrahedral, square, planar, or um, tetrahedral, square, or octahedral. Why they are forming only these kind of geometries? Why? He could not explain these points, and these are considered as the limitations of the Werner theory. So we'll discuss all this in the next video, most probably. So the let's move forward to some other concepts like what is a homolactic complexes. This is not a part of the Werner theory, but Let us study some other terms like homoleptic complexes. Homoleptic complexes are basically those where in which metal ions is coordinated to bond a one kind of donor atom. Homo means similar. Okay. Homo means one or similar, basically similar, uniform, you can say. So, cobalt over here is binding to only one type of ligand, that is ammonia. All six are ammonia only. So these kind of complexes are called homoleptic complex, while heteroleptic complex are those where there are there are more than one kind of donor atoms. For example, here four ammonia molecules are coordinating and two chloride ion are coordinating to the cobalt. You can say four are ammonia and two are chloride. Nitrogen, nitrogen, these nitrogens are for ammonia. These and here in this complex, five ammonia molecules are coordinating and one bromide ion is coordinating. So such complexes where different kind of metal, where different kind of ligands are coordinated to the metal, these are called heteroleptic complexes, and where only one type of ligand is coordinating to the metal, that is called a homoleptic complex. Next, we'll do some examples how to calculate the oxidation number of central atoms. The oxidation number of central atom in a complex can be defined as the charge that it would carry if all the ligands are removed along with the electron pairs shared with the central atom. So basically oxidation number of the central atom we need to calculate, that is equal to the when every ligand is removed and every counter ion is removed, the individual charge on the metal. So find out the charge on this complex. Considering the cobalt chloride ammonium complex, calculate the charge. Cobalt chloride ammonia plus. So how will you calculate the charge over this? As you can see there is overall plus one charge. Okay, overall plus one. So let us consider X as a charge for cobalt. X is the charge for cobalt. Plus there are two chloride ion and each chloride has an ion has a charge of -1. Ammonia is a neutral ligand, so 0 into 4. Okay, and it has a equal to overall charge of +1. So solving this equation, x minus 2 plus 0 is equal giving to +1. So x is equal to +3. That means the oxidation state for cobalt over here is +3. Okay, so please do solve the other example. I'll give you 1 minute and then I'll solve the second one. I hope you guys have started solving the second example. Let me also just start. Do not copy and try to do it by yourself only. So let's just see how much you understood. So let's say I'm starting right now. Please check your answers. Let's say cobalt has oxidation state of X. Plus, how many molecules of ammonia are there? 5. What is the charge of ammonia? 0. Ammonia is a neutral molecule, no? Plus, how many bromide ions are there? 1. What is the charge on bromide ion? -1 into -1. So, overall, this is the charge and it is equal to, what is the charge on this ion? +2. So, x plus 5 into 0, 0. Minus 1 into -1, 1. Equal to +2. What is the charge? +2 plus 1. It will go in this side now. +1. X is equal to +3. So the charge on this cobalt is +3. Good. Solve the third example. The third example is cobalt, ammonia 3, 6 plus 3. So let's say cobalt has oxidation state of plus 3, cobalt has a plus 3 charge plus X charge. Okay. How many molecules of ammonia are there? 6. 6 into what is the charge on ammonia? 0. It is a neutral molecule. No other ligand is present. Overall charge is plus 3. X plus 0 gives plus 3. So X is equal to plus 3. That means cobalt over here has plus 3 charge. Okay. One more example. Let's say we'll do PtCl4, K2PtCl4. Okay. Solve this example. So what does K2PtCl4 means? K2PtCl4 means if there are two K positive ions plus PtCl4 minus 2 as a negative ion. So what is the charge on this platinum? Let's say platinum has an oxidation state plus X plus 4 chloride ions are there. 4 into minus 1 equal to total overall charge is equal to minus 2. That means we have X minus 4 equal to minus 2. X is equal to minus 2 plus 4. X is equal to plus 2. So platinum over here has a charge of plus 2. I hope you guys understood. So summary for this video. In this video, we discuss Werner's theory, Werner coordination theory. Werner was a scientist who, a Swiss scientist who is known as the father of the coordination complexes. He obtained a he got a Nobel Prize in 1913. He gave a theory that contains postulates like a metal complex contains primary valency and the second valency. Primary valency are the ones satisfied by the counter anions or the outer sphere ions, and the secondary valency are the one which is directly coordinated to the metal complex. That is, these ammonia molecules both can satisfy the positive charge on the central metal atom. So evidence that he provided to favor his theory were cryoscopic measurements. Cryoscopic measurements being a colligative property, delta TF depends upon the number of moles. So depending upon the number of moles that he was getting, he found out the different values of delta TF for different complexes. Also, he performed electrical conductance measurement. Electric conductance measurement current, that is I, is again proportional to the number of ions. So, depending upon the more the ions, more was the current. So, for the different complexes, he obtained different values of current, and that's how he explained his coordination theory that some ions are present outside that are ionizing, that are ionizable, and some are present inside. That's why the values are coming different. The third and the most important one evidence that he's provided was precipitation reaction. He added silver nitrate to the reaction mixture that contained coordination complexes, and depending upon the X amount of silver chloride that he was getting, he concluded that only X amount of chloride ions are present outside. Only that amount will form precipitate. And he further explained he and we came to know that the limitations of but there are certain limitations. This theory came in 1913, more than 100 years back. So eventually over the time people understood that there are some issues with this theory. This theory could not explain the magnetic properties could not be explained, color could not be explained, and why the only the octahedral arrangement or tetrahedral arrangement or square planar arrangement is there. Why only these arrangements are there. He could not explain these points, so this was further explained by valence bond theory that we'll discuss further in the part 3. Uh, I'll upload the next video soon. Hope you like it. Thanks for watching.